Okay, welcome everybody. I am in my basement. I spent money and time putting up this wall, this board. I wish I could turn the camera around so you can see what I'm looking at here, but it's been a blast the last couple of days. I can't see the computer. I have a laptop that's kind of far away from me, so you guys. The microphone, the audio on the computer, the speakers they're not that good. I'm going to get another set of speakers. But you guys can open your mics when you want to make a comment, ask a question, or help me with calculations. I'm going to wait a few more minutes. I think I have, it's about 15 people signed in. We'll give it about another 2 or 3 minutes and then we'll get started. So while we're waiting, I've been experimenting with lights. I know there's some glare. I have 3 lights up, and I know there's some glare from this overhead light and a little glare from the one over there. Can you guys see the board okay?
Yes.
Okay, was that Kevin?
Yeah.
Okay, let me see if I can adjust the audio a little bit. So this will be kind of trial and error. I'm getting feedback. Test 1 2, testing 1 2. Okay, this is going to be trial and error. I'm going to try to get the lighting right and the audio right, but the room is pretty small that I'm working in. The space is really not ideal for what I'm doing. But as I said, I put these boards up. It's been kind of crazy the last couple of days. I spent a lot of money and a lot of time trying to move the recording situation from the school to my home. There's really no space here in my home, so I got a corner in the basement where I am. So if you hear dogs or traffic or kids running around, well, it's because I'm at another apartment building in the basement. We're going to go ahead and get started. I want to talk about a couple things. Last video, I know, well, first of all, before I get into that, I think I might have the links to the video screwed up on Blackboard. I didn't have a chance to check them thoroughly, but if you have any issues, I think I might have linked to the same video twice. I'll check that out after I'm done here with this recording, and after I get it posted, I'll get that straightened out. So if you had any issues, let me know. But what I want to do is talk about something that's really important. Actually, we're going to talk about 3 different ways to solve circuits that have more than one voltage source. Now, let me explain what I mean when I say that. If I have a circuit, and guys, if one of these markers don't show up, let me know if you have a problem seeing anything. So if I have a circuit, and if I have something simple like this, so I have a voltage source like this, and a voltage source like this. And I can have any kind of circuit out here. Doesn't matter what it is. So I can have something like that. And let's say this is, let's just say this is 10 volts, and this is 6 volts. If those voltage sources are connected directly in series, or anywhere in this line, if you notice the polarity on each of these, they're opposing. We talked about this kind of connection. It's called series opposing. So this is plus, minus, minus, plus. Basically what you can do here is not that difficult. You can take these 2 sources and you can combine them. Since they're opposing each other, the net voltage would be the difference of the 2. If I flip the 6 volt source over, that would have a series aiding situation, and the net voltage, the total voltage, would be the sum of the two. But since they're opposing each other, I could easily erase this. I can replace this with a 4-volt source, and if I knew the value of these resistors, I can solve them. So that's pretty easy to do. If I have more than one voltage source or current source, and they're connected, the voltage sources are connected in series, I can either add them up and subtract them, or subtract them and replace them with an equivalent voltage source. What if I have a situation like this? A situation where those sources are not connected directly in series to each other, so I don't really know how to combine them. As a matter of fact, when I have a situation like this, I can't use Ohm's law directly. I can't use Watt's law. I can't use any of those laws directly to solve this circuit. So what we're going to do is spend some time looking at 3 different ways to solve circuits with multiple voltage sources or current sources. We'll say multiple power sources. The first way we'll look at is what is called superposition. We'll look at another method called mesh analysis, and then we'll finish up looking at another method called nodal analysis. My hope today is to do a superposition example and a mesh example, and then we'll probably end up running out of time and we'll do nodal analysis in the next video. So I want to talk about superposition. Let me get my markers together because half of them don't work. I want to make sure I have all good markers. Okay, I think those are the only 3 that you guys can see, so I might be able to see the blue. We'll try that. All right. So I want to talk about superposition. And superposition is a theorem. I'm not going to quote the theorem. I'm just going to show you how to do it. I want to show you how to think about it. So superposition comes from kind of a play off the word superimpose. Consider this circuit right here. I have a voltage, some kind of power source on the left providing 5 amps. I don't know what it is. It could be a voltage source, it could be a current source. But I know that power source is providing 5 amps to the right. I have some other unknown power source over here providing 3 amps to the left. I want you all to calculate the voltage across the resistor with polarity. I'll give you a second. I want to know the voltage across the resistor with polarity. When you get an answer, let me know. How would you calculate the voltage across the resistor? You're going to have to use your audio, not your, because I can't see if you text me, I can't, if you send me a message, I can't see it. The computer's too far away. So how would I find the voltage across this resistor? What would I do?
Would you use multiply the 5M with the 5 amps with 10 ohms, and then multiply the 10 ohms with 3 amps, and then add them together?
Okay, so if you guys, I'm assuming, can hear each other. The way Kevin just described it is basically superposition. And I'm going to talk about that. We'll talk about that in a second. So yes, Kevin, that is the way, that is a way you can do it. Is that the only way you can do it? What's the most direct way to do this problem? How much current is actually flowing in the resistor, and what direction does that current take? How much current is flowing in the resistor?
The net number of amps is 2.
The net number of amps is 2, and it's 2 amps at 5 amps this way, 3 amps that way. The actual current in the circuit is 2 amps like this. And I think everybody will agree with that. It's 2 amps to the right. Matter of fact, there isn't really 2 currents in the resistor. Even if I have a power source providing 5 amps to the right and a power source providing 3 amps to the left, there's still only one current, 2 amps to the right. And so if I know the net current flow through the resistor, I know the value of the resistor, it's easy for me to get the voltage. I just take current times resistance, I get 20 volts. And what would the polarity look like? Is this side positive or is this side positive?
The left side is negative. The right side is positive.
Okay, actually it's the other way around. So this is positive and this is negative. So the way we define polarity across a resistor, if I have a resistor, if current flows this way, then the polarity is like this. If current flows the other way, then I will swap the polarity. So the point I was making is you can get this directly. If I know the net current in the resistor is 2 amps, I know the value of the resistor is 10 ohms. It's just a simple Ohm's law problem. I got I times R, I get 20 volts. Now, Kevin, you said something interesting though. What Kevin said earlier, his first statement was, if we wanted to, instead of doing it like this, we can actually figure out the voltage due to the 5 amps, treat that all by itself, and then figure out the voltage due to the 3 amps, treat that all by itself, and then we can combine the two. Let's do it that way. If I only look at the 5 amps, then what I have is 50 volts. I got I times R, I get 50 volts. But notice the polarity. This end is positive, this end is negative because of the way we define a polarity across a resistor. If I only consider the 3 amps, again, I got I times R, I get 30 volts. But this time, the polarity is positive on this side and negative on the other side. So basically, here what I have, if I superimpose these two answers, superposition means I superimpose the answers. I can actually take let me get rid of this, 50 volts from here, and this polarity, and the 30 volts from here, and this polarity. And since these don't match up, positive and negative, they're opposite, this is actually series opposing. So I would subtract these, and I would say 50 minus 30 is 20, and I get 20 volts that we knew existed across the resistor from the get-go. So you might wonder, okay, well, why go through all that work when I could have just did what I did at first, figure out the net current, multiply the net current by the resistor value, and get the voltage directly. The point of this example was to show you that either way is correct. I can actually deal with the net current in this case, or what this is teaching us is that I can take the current voltage from each source independently and I can combine those. And that in essence is what superposition is. What we do is, if I have a circuit with more than one voltage source like the one I have here, what we'll do is we'll turn one voltage source off and treat the circuit as if it only had the one voltage source in it, in this case, this one. We'll solve all currents and voltages. And then we'll turn that one back on and turn the other one off, and we'll solve the circuit. And then we'll combine the two, just like we did here, and the net voltage or current will either be the sum or difference of the currents and voltages in the circuit, depending on current directions and polarities. If the polarities are the same from the two sources, we add them. If they're opposite like this, we subtract them. If the currents move in the same direction, we add those. If the currents move in opposite directions, the direction will subtract them. And so what I want to do is I want to show you or demonstrate superposition on this circuit right here. So this is something that you really want to work along with me on. So if you don't have pen and paper, calculator, go ahead and take a second and get that while I clean the board up. And we'll walk through this. Now, The one thing about superposition is you're going to have to draw the circuit over and over again. Basically, you'll have 3 diagrams, possibly more. You'll have the main diagram, a circuit, and then you'll have one circuit for each voltage source. And you may have more than one, depending on how complex your circuitry is. You might have to reduce it and draw several circuits, several equivalent circuits. So here's a method of superposition. So make sure you have pen and paper, and I want you guys to try to work ahead of me. So what I want you to do is, what we're going to do is, first is I'm going to name this right here. And that's just for convenience. That's A, and that's B. I'm just doing that for convenience, just so we can talk about that, the node A and B. Now, what I want you to do is to draw this circuit turning, let me name these. This is B1 or BS1. This is BS1. Okay, so I want to turn BS2 off, leave BS1 on, and we're going to solve the circuit with only BS1 in the network. So what I want you to do now is to draw the circuit turning BS2 off. How do you turn a voltage source off? How do you get rid of a voltage source? What do you have to do?
Short it.
You short it. It's just like when you Thevenize, it's the same exact thing. When you Thevenize, if you deal with voltage sources, you replace it with the short to set it with zero, to set it to 0. If you have a current source, you replace it with an open. In this case, we deal with voltage sources. So I'm going to short this out and draw the equivalent circuit, and then we'll solve the equivalent circuit. So I'll be quiet for a second. You go ahead and draw what you think the circuit looks like, and then we'll solve it. All right. If you replace this with a short, if I short that out, then if you notice, R3 and R2 are already tied together at the top. But when I replace this with the short, I'm now connecting the bottom of R2 and R3 together. So I end up with this circuit. And hopefully you can clearly see that if I replace this with the jumper wire with the short circuit, then that makes R3 and R2 in parallel. So your equivalent circuit should look like this. And if I bring my node information over, again, that's just for convenience. A is right here, and B is right here. The next thing you do is you get an equivalent circuit by combining R3 and R2. So go ahead and do that, and then we'll do the math on that equivalent circuit. So if you combine those, you go ahead and draw it on your paper. If I have 6 in parallel with 3, by now you should know that's 2. We use those numbers all the time. So this is the combination of R2, comma R3. And then my node A is right here, and B is right here. All right, so let's solve this circuit at the bottom. what we're looking for over here are current directions in each resistor. So we're going to solve this and work our way back over to this one. And then we'll change the sources around and we'll see what we get when we turn the 84 volt source off. So let's see. I don't know how you want to do it. I'm going to use the voltage divider rule here and just figure out the voltages and then we can get the current. However you do it is fine. I like using the voltage divider rule. Now you guys will have to help me with the calculations because I don't have a calculator. But if I want to know the voltage from A to B, let's see. Hopefully you guys can see this. VAB 2 on 14 times 84 volts. So I'm using voltage divider rule to find the voltage across the 2 ohm. What's 84 divided by 7?
12.
All right. I'm trying to get these colors right. All right, so somebody said it was 12, so this is 12. This is 12. Now this actually extends all the way across here. I want to show that. And then this is 12 from A to B. And if this is 12, then this has to be 72 across this resistor. So I got 72 volts from there to there. Okay, well, that's not too bad. We can easily get the current here. 12 on 6 is, I got 2 amps. And actually, I've done something wrong. Notice the polarity of my voltage source. So I'm drawing that 2 amps this way. Actually, the current is flowing this way. So I made a mistake there. So don't make that mistake. Because superposition depends on direction of current and polarity of voltages. So you got to get that right. So actually, I do have 12 on 6, but because the positive was here, the main line current is coming this way. And it's going to split here and here. So I have 2 amps going up like that. And over here I have 4 amps going up like that. And that means that the sum of these, 6 amps, is flowing like that. So what I want to do over here is I want to show the current directions, and these are the current directions from voltage source 1. I'm going to show those in this original diagram. So I'm going to erase the board up. And what I can say is, as long as my math is right here, what I can say is the contribution, or I should say the current values and directions for the 84 volt source with the 21 volt source turned off would be as shown. The 84 volts causes 6 amps to flow in this direction. So R1 has a current of 6 amps to the left. R2, 4 amps to the left. R3, 2 amps. Towards the top. So I got 6, I got 4, and I got 2. So now what you need to do is the same thing. I want you to turn VS1 off put BS2 back in the circuit and figure out the current magnitude and direction for BS2. Go ahead and do that on your paper. I'll give you a second to do it. If I replace this with the jumper wire, then that connects R1 and R3 in parallel, and what I have is 12 and 6 in parallel. 12 is R1, and 6 is R3. And then I have R2 here, 3 ohms. And I still have 21 volts. And here's my A, and there's my B. So go ahead and get the equivalent circuit for this. Can somebody give me 12 parallel 6?
4.
All right, so you end up with this circuit. Looks like we have a total resistance of 7 ohms. So I have 3 amps of current flowing. I'm just going to show that with this blue. And if I have 3 amps of current flowing in the circuit, that means from the voltage from B to A would be 3 times 4, which is 12. So I got 12 volts from A to B. I have 9 volts across this one. So I want you to figure out the current values and directions based on those numbers. Over here is pretty easy because I got 12 on 12. Now again, notice the direction is important. Notice the direction of that voltage source. If I flip it over, I have to draw the current going to the top. But the way it's drawn here in the circuit, then the current is actually coming towards the bottom and going up this way to those resistors. But either way, I got 12 volts divided by 12 ohms. So I have 1 amp flowing up like this. And I got 12 on 6. I got 2 amps going up like this. They meet together at node A, so I got to have the sum of the two. I got to have 3 amps flowing through R2, but we knew that from down here. Now, here's the important thing you got to do. And hopefully you can see the difference in these colors. I'm going to get a green marker, and the original currents from the first circuit from the 84 volt source, they're shown here. I got 6 to the left, 4 to the left, and 2 towards node A. So what I want to do now is show these currents from the 21 volt source in this resistor. It's going up, so that means I have 1 amp going that way from the 21 volt source. And then here I have 3 amps to the right. So I got 3 amps to the right from the 21 volt source. And the only thing I'm missing is the current through R3. Well, I'm showing that going to, what did I do here? Oh, I already got it. I got 3 amps. I got 1 ounce, and I have the 2. So I have the 2. What am I missing? I have actually 2 2 amps on it. Because this was 2, and then I had another 2 amps going up. I had 2 from here, and then I had 2 from the other circuit. Let me just check to make sure my notes are right.
Mr. Singleton,
Yep.
how were you able to get 4 amps as the second current source?
Hold on a second. Okay, say that again.
How were you able to get 4 amps as the second current source?
Over here.
Yes.
How'd I get? Wait a minute, I'm having issues here. Hold on a second.
Like how were you able to solve it?
Okay, you're talking about the 21 volt source?
Yes.
Is that Jay?
How were you able to find the second current?
How do I find the second current?
Like how you get 4 amps as the second current? Like it's a total current for like the voltage for the second voltage source.
Are you talking about the 21 volt source?
Yes.
Okay, so I didn't get 4 amps for that, but I had let's just go back here. So let me get rid of this. So I'll go back. So if we go back down here, does that make sense down here what I did? You see how we got to this step?
Yes.
Okay. Well, if you see how we got to this step, by combining these 2 resistors, we got 4 ohms. We still got this one, and that was R2, by the way. So if you follow how we got to here, we'll just work backwards again. So we said that you agree that the total resistance was 7, all right?
Right.
Let me just clean all this up. So we'll go back.
Hey, Jalen, the 4 amps was from the 84 volt source.
Is that what you're asking? Let me just walk back through this so everybody can see. I don't
Because
know.
it's
I
not
have a hard time hearing, and I don't have a lot of room on the board, so I don't want to confuse anybody. But if everybody can see how we got this, I think that was Jalen. I'm not sure. I can hardly hear the computer. But if you agree here with this circuit, then clearly the current is 3 amps. I got 7 and the 21 is 3. That means I got 12 volts across A and B, and I got 9 volts across this. And then we move that up to here. I didn't put my 9 volts over here. And then the current direction here through R1 would be the 12 on 12, right? Which is 1 amp. So I have 1 amp flowing actually this way because the direction of my current is actually like that. And that's what I was showing right here. I have that 1 amp. I think that was Jalen. So that takes care of that one. I have 12 on 6. So again, I have this time 2 amps flowing that way. So that was the 2 amps here. And then they come together at node A. So I got to have 1 amp and 2 amp. They come together and actually flowing this way through the battery. That's the 3 amps that we got down here. So I have 2 amps going up through R3. So both of these 2 amps are going in the same direction. So one of the 2 amps was from the 80 volt, 4 volt source. The other 2 amps was from the 21 volt source. So I think all of our numbers are right. So what we have to do now is, if you follow that, we have to consider the direction of the current. If they're going in the same direction, we can add them. If they're going in opposite directions, we're going to subtract them. So go ahead and do that. What we're looking for is the net current through each resistor. Guys, I'm baking under these lights. I don't know how long I'll be able to perform like this. I got you can't see it, but I got a big light over here, and I got a big light over there, and I got a fluorescent light above. You can probably see the reflection in the board, but I don't know how people do it who really go on camera and do this for a living. I have to get a fan down here. Anyway, I don't know if this red is going to show up. Hopefully it does. I don't think it showed up before. But the whole point of this is this. If you can eliminate one of the voltage sources, then basically you can solve a circuit, because that's what we've been doing all semester. Anybody can solve anybody should be able to solve you guys should be able to solve a simple circuit like this if I take one of the voltage sources out. You can find all the current directions and magnitudes. The key here, though, is if the currents are going in opposite directions in the actual circuit, then I'm going to subtract the two. So the actual current flow in R1 would be what? What's the magnitude of the current in R1 and direction, according to what I have here? I have 6 amps to the left. I have 1 amp to the right. So that means that I actually have 5 amps. Let's see if I can shade this in. I got 5 amps in that direction because I gotta subtract those two currents. Same here. I have 4 amps to the left. I got 3 amps to the right. They're going in opposite directions, so I have to take the difference between the two. The actual current flow is in the direction of the larger current, so I would have 1 amp. Going like that. And then here, notice both currents are going in the same direction through R3. So whereas before I subtracted the two, here I'm going to add them. So I'm going to have 4 amps going up like that. I don't know if you can see this red or not. So I got 1 amp, I got 5 amps, I got 4 amps, And at this point, what you could do is, I didn't ask for it, but if I ask you for voltage drops, then that's easy. It's really easy. It's just I times R. The only thing you got to be careful of is that you get the polarities right. Remember, the direction of the current determines the polarity. So if I ask for voltage, and here I can say, well, I got I times R, and it will be 60 volts, positive, negative, like that. But once you get the current, you can solve for anything, power, whatever. Okay? So that's superposition. Now the problem with this is you have the original picture you have to draw. Hold on a second, I'm burning up here. You have the original picture you have to draw. And then you'll have a picture for every source that you turn off. And you see that if I have a complex circuit, I may have to redraw like I did over here. And this really wasn't that complex. So I think the thing that I like about superposition is once you get the analysis under your belt, it's pretty intuitive. I mean, if I got two currents going in the same direction, I'm going to add them. If they're going in opposite directions, I take the difference between the two. You can't be any more direct than that. And once you get the net current in the resistor, you can find the voltage across it, and you can find the power dissipated by it because you know V and you know I. So that's a piece of cake. So the advantage of doing this, I think, is very, very, very intuitive. You can kind of see what each source is doing. The disadvantage is, you see, I need a bigger board, and the space I have here is really not enough. I need a big board like we have in our classroom. And so you got to keep drawing these pictures over and over and over again. So it would be nice if we had a method that we can apply to just the circuit. We wouldn't have to keep drawing a lot of circuits. Let's just let the math do the work for us. And so that's what I'm going to show you next. It's called mesh analysis. Now, you guys write the answers down to this because we're going to do our mesh analysis on the same circuit, and hopefully our answers agree with each other. If not, then that means you made a mistake either here or with the mesh. So here we got 5 amps to the left in R1, 1 amp to the left in R2, and 4 amps going up in R3. And that's superposition. I'm going to clean the board off, and I want to rework this another way. Now, this is in your book, and here's the thing. Some of you guys go to YouTube, and you'll see there's different ways you can apply methods. I'm going to show you a way, and then you can go to YouTube, or you can pick up somebody else's book, and they can tell you. It'll be the same thing, but it might be a little bit different. And I just don't want you to be confused. So as long as you, whether you use the way I'm going to show you or you use another method, as long as you're consistent, you should be okay. But I think the way I'm going to show you should be pretty straightforward and direct. So let me put the same circuit back on the board. All right, I think this was 84. And this was 21. Let's see. All right. So here's a circuit we had before. I'll make sure I got the values right. 12, 3. Yep, I think that's right. Okay, so this is mesh analysis. And the word mesh comes from the fact that when you have like a really, really complex circuit, it looks like a wire mesh fence. So they call it mesh analysis. Now, if you take a look at this circuit, how many loops do you see? How many loops do you count in the circuit? How many loops?
3.
3 is
Say about
correct.
2.
Some people say 2, some people say 3. There's actually 3 loops. Here's a loop, here's a loop, and the third loop is the outside loop. All right, so a window, I don't know how to explain it, but I'll say it like this. There's 3 loops, but 2 windows. Here's a 1 loop, 2 loop, but here's window 1, here's window 2. If I put another resistor up over here like this, then there will be, let's see, 1 loop, 2 loop, 3 loops. There's a loop around the outside, but there's 3 windows. Does everybody see what a window is? Basically, one of these rectangles or squares is a window. Now, the reason that's important because with this method, what you'll end up with is an equation for every window. Not every loop, but every window. We have 2 windows, so when we solve this, we'll end up with what we call 2 loop equations. If I had this one where there's 3 windows, we'd have 3 equations. If I have 4, we'd have 4 equations. We have a 2-window circuit. So make sure you have pen and paper, and I'm going to show you the way I approach problems like these when I do mesh analysis. Write the steps down. The first thing we're going to do is we'll name the windows. We'll call one window A and the other window B. And we're going to have something called a loop current. We're going to imagine a current flowing in a loop around either window A or window B. The loop current can go either clockwise or counterclockwise. Doesn't really matter. But for what we're going to do, we're going to make all of our currents go clockwise. Doesn't matter, the math will work out either way. But for ease of grading and just so our answers agree and the math agrees, what I want you to write down, if you're writing down the steps to solve this problem using mesh analysis, name each window. We'll call one window A, B, C, and so forth. And then in this window, then the current, name of this current would be IA. So here's IA, and here's IB. And the loop currents, I'm actually going to draw a loop like this. Just draw a loop. That represents IA, and that represents IB. And again, you can draw these loop currents any way you want. I could have put IA the other way, and it doesn't really matter. But what I want you to write down, and what we'll do when we do this method, we'll name the windows, A, B, C, and so forth, and then we'll draw on our loop currents, and we're going to make all of our loop currents go clockwise. That way we'll get the same exact equations. Now, if you notice, because of the way I have the voltage sources, I know the polarity of the voltage sources. I mean, I know that this is positive and that's negative because the longer line is on the bottom, and the same over here, right? But the polarity across a resistor, as we said in class many, many times, has nothing to do with these polarities. The polarity across the resistor depends on the direction of current flow. So if I choose IA to go clockwise, then that would mean that this side is positive and this side is negative. But if I had chosen it to go the other way, then I'd have to reverse these. It would be like that. So the voltage across the resistor depends on the direction of current through it. So I'm going to name the little windows A and B, loop current A, loop current B. I'm going to assign loop currents in each window in arbitrary directions. It doesn't really matter the direction. But what we said was, for this class, what we're doing, we're going to make all of our loop currents go clockwise. So when you write your notes, say in your notes, we'll make the loop currents go clockwise. Once I give the loop currents a direction, then I can put the polarities across the resistor. So I'll be quiet for a second. I want you to put the polarity across R1, R2, and R3. put the voltage polarity across each of those resistors. So because of the direction of my loop current, R1, loop current is going that way, right? Loop current is going clockwise, so the current is going that way. This would be positive, and this would be negative. And same here, the loop current here is going that way, so this would be positive, this would be negative. Now I got a problem with R3. The problem with R3 is both loop currents go through R3. So how do I write polarity across a resistor if I have two loop current through the resistor? Well, the answer is what you do is you ignore one window and just look at IA, act like IA was the only current flowing in the circuit through R3. If that was the case, if I ignore IB, then IA is going this way, so this side, or the top of R3 would be positive and the bottom would be negative. And then you come over here and do the same thing for IB. We just ignore IA, and we say since the current is going up this way, this would be positive and that would be negative. Now I'll pause for a second because it can be kind of confusing, but if you think about it, it really isn't, because all you do is just act like you have a series circuit, and this would be plus minus plus minus. And if I act like I have another series circuit here, current is flowing this way, it's going to be plus minus plus minus. So the only thing you got to do is remember, if you have a loop current with two loop currents in the same resistor, you always have opposite, as long as you assign your loop currents to go either both counterclockwise or both clockwise. We're doing clockwise here, but it could go the other way if we wanted to. So as long as both loop currents are going the same direction, you'll always have a situation where the polarity through a common resistor will be opposite each other. So hopefully that's clear and not confusing anybody. So all we've done now is set this off to be, we just set this problem up to be solved. Now what I'm going to do is I'm going to go around the circuit. I'm going to start at a certain point. Anywhere I want, I'm going to start. I'm going to go around the circuit, and I'm going to write down the voltage rises and drops. Now we talked about what a voltage rise is and what a voltage drop is. So let me just remind you that if I have some kind of element, and let's just say, let's just call it V. If I have element V, and say the polarity is like that. If I'm going around this way, I'm going from a low to a high, and I write that as a rise. That's a plus V. So that was 10 volts, that would be a plus 10 volts. If I go the other way, if I go from a high to a low, then I write that as a minus V. The way to think about it is, whichever way you're tracing the current flow, in this case it's going to be clockwise. Whatever the last sign is you're pointing to, it's going to be the sign of your turn. So I'm going this way, I'm pointing to the plus sign, that would make it positive. But if I was going the other way, I would be pointing at the negative sign, that would make it negative. So we're going to write down all of the voltage rises and drops as we go around each one of these loops, each one of those windows. The problem is we don't know all the voltages. I mean, we know this voltage and this voltage, but I don't know V1, I don't know V2, I don't know V3. So how am I going to write the voltage drop or voltage rise if I don't know the value of those voltage drops? And the answer is, Ohm's law says that voltage is equal to current times resistance. So what we're going to do is we won't worry about the I part. We only worry about the R part. That's the given. So in other words, for this one, V1 would equal I1 times R1, but I don't know I1, so I'm just going to not worry about it. I know that's a 12 for that, so I'm going to write that. I'm going to write that as 12 IA. If I nearby A, I can multiply the 12 ohms times whatever IA is and get V1. We're going to write the voltages in terms of resistance and current, in other words. That's how we're going to do it. So I'm going to do the first one really, really slow so you can see what I'm doing. You can kind of follow me. So what we're going to do is start in any corner. I'm going to start in the lower left-hand corner. I'm going to go around this loop and keep track of my rises and drops. And you just kind of watch how I write these when I do it. So this is for IA. So I'm going to put IA here. So if I start right here, I go from a plus to a minus. That's a drop of 84. So I'm going to write that as a minus. I think I'm going to run out of room. Let me move this over. I'm going to write this as a minus 84. So I drop 84. Here I go from a plus to a minus. So that's a minus 12 IA. I don't know V1, so I'm writing V1 as I times R. Just using Ohm's law, I'm writing voltage in terms of current and resistance, but current is my unknown here. So that's where I get the 12 IA and this minus, because I got a drop. Now, notice where we are now. We're at that one resistor where I have two currents going through it, and that's a problem. How do I write it? I can see just from the picture, the way I drew IA is going this way, and IB is going up. So everybody can clearly see that those two currents are subtracting from each other the way I have them drawn in this diagram. The problem is, do I subtract like this? Is it IA minus IB? Or is it the other way, IB minus IA? And the answer is, I really don't know, because I don't know which one's bigger. I don't know. I don't know which one of these to use in my math. So here's what we're going to do. Whichever window we're in at the time when we're writing this equation, we're going to write that term first. So since I'm in the IA window, I'm going to write IA first. I'm going to use this one. But in a second, I'll be in the IB window. When I get to that resistor, I'll use this one. So write that down if you're keeping track of the steps. Okay, so I started here. I'm going around this first window, keeping track of the rises and drops. I go from a plus to a minus. That's a drop of 84. So I wrote minus 84. I go from a plus to a minus. That's another drop. So I got a negative sign. And then it's resistor value times the current. So it's 12 IA. So I got a minus 12 IA. And now I get to this resistor where I have a share. I got two currents in it. So either I'm going to write IA minus IB because the currents are going in different directions. I'm going to write the reverse, IB minus IA. And what I said was, whichever window we're in front of, we're going to write that current first. So I'm looking over here. Ignore this window. I got a plus to a minus. It's a drop. So this is a negative. I got a 6. So I got a 6, comma. And this is going to be IA minus IB. I'm writing IA first because I'm in the IA window. And I don't have enough room to write it, but all of this has to equal 0. So you can write it on your paper. So does anybody have any questions on how I came up with that equation? Because this is the hardest part right here. Does everybody see what I did here? Anybody have any questions? And I got to walk to get close to the computer because I can't hear if anybody has anything. Is everybody okay?
So it's either this method or the disposition. It's not like we need to know both. There's an either or type
I'm
of
actually
thing.
going to show you 3 methods. I've showed you one way, superposition. I'm showing you this way. We won't have time to do it today, but I'll show you another way next time we have a video, I guess Monday. Basically, there's more than 3, by the way. There's other ways I could show you, but the 3 main ways: mesh analysis, the other was called nodal analysis. We'll do that Monday, and superposition. It's like having different tools in the toolbox. Sometimes it'll be easier to do this way than superposition. Sometimes superposition will be easier. Sometimes it just depends. It's like having different tools for different jobs. So it's not either or. It's you're going to learn all three ways, and then on the exam I might say solve this circuit using this method. Then you got to use that method. Or I might say solve this circuit using superposition. Then you would use superposition. But the more tools you have in your mathematical toolbox, the better. And if you are, I don't know, some of you are electromechanical, but if you take electronic courses, sometimes they use superposition a lot to prove things. You'll need that. I know when you deal with amplifiers, you'll see that often when they go through the talk about how different amplifiers work and give you proof. So they tend to use superposition. But does everybody see how I got this equation? I don't want to run out of time. We got about 20 minutes. If you're okay with it, I'm assuming since I don't hear anything that you guys are okay with it. Go ahead and clean the equation up, combine like terms, and then I want to write the loop for the other one. So let's go ahead and make sure we end up with the same thing. Just see, I got 12IA. I got minus 6 here, right? I have minus 6 times IA. I got minus 18 IA. And I got minus 6 times a plus 1. I got a minus times a minus is a plus 6 IB. And I'm going to take the 84 volts and move it to the other side. That's going to make that a positive number. So I got to erase the board. I just don't have a lot of room here. But I want to make sure that this is the equation that you guys got. Does that look right? When you combine everything, is that what you got? That's what you should have. Now, you guys agree with that? If you see how we got this, and what I want you to do is, I'll be quiet for a second. Go ahead and write the second loop equation. Write the loop equation for IB, or I'll be quiet and let you do it. Okay, now when you write the second loop equation, you really can start anywhere. You can start here. It doesn't matter where you start. The only rule is you have to start and stop in the same place. So I always, when I do it, I'll start in the lower left. And I'll stop in the lower left. I'm going to start right here in the lower left. And I'm going to trace the loop occurring around window B. I got two sets of polarities, and since I'm in window B, I'll ignore the polarity over here in window A. I'm only focusing on the plus minus here caused by IB. If I go around clockwise, I go from a plus to a minus. That's a drop. So I'm going to write that as a minus 6. But this is the resistor where I had two currents in it. So when I have two currents in it, I got to write it either IA minus IB, or I can write it like IB minus IA. And what we said was, whatever window we're in, we'll write that one first. So when I was in the IA window, I wrote IA first, and I'm in the IB window, so I'm going to pick this one. So I got a drop of 6 times IB minus IA. And that puts me right here as I go around the loop. This is another drop minus 3 IB 3IB, and I go from a minus to a plus, so that's a rise. That's a plus 21. I'm sorry I don't have room to write it. So that if you clean this up a little bit and you do the math, combine like terms, you should come up with, okay, I got a plus times, I got a positive 6IA. I guess I better do it all in black. So it looks like I got 6IA. I got a minus 6IB here, and I got another minus 3 there. That's minus 9IB. And I got a positive 21. When I pull across the equal sign, I get a negative 21. So here's what I got for my equations when I go around the loops. Just make sure that agrees with what you have. Now, I think this is, like I said, this is the loop equation, setting it up, getting these equations is the hardest part. I don't think it's particularly difficult. You just got to pay attention to each step. Once you end up with the loop equation, now we got to solve it. Well, we got 2 equations and 2 unknowns, so you got to solve it some kind of way, and you know multiple ways to solve stuff like this. We talked about some of that last time we met. We're going to use a method of determinants. You may be tempted to use some other method, but I want you to use determinants only because when we go to more complicated circuits, determinants turns out to be the easiest way, and they're actually pretty fast. So if everybody agrees with this, we did a couple practice problems, and I told you I would give you some practice homework for determinants and for some superposition, but that's when they kicked me out of the school. I had it set up where we were using a room 203 to do the video, and I was getting comfortable there at the whiteboard and everything going on, and then they came in and said that we had X amount of time to get out. So I literally grabbed my stuff, threw it in the car. I made PDFs of as much stuff as I could, and then I figured out how I was going to deliver the videos and ended up down here in the basement. So I didn't have a chance to make some of the sheets that I wanted to make for you, but hopefully from the 2 practice problems that we did, you can see how to set it up. Now we're running out of time, so I'm going to go kind of quickly. Set this up in a determinant. If you looked at the last video, if you were with the last lecture, you know we call one of them D. And just to remind you to get that, all you do is you make sure that your coefficients are lined up in order, and then you write down the value of the coefficient for each variable. So I write down the 18 and the 6. So I got a minus 18. I got a 6. I got a 6, and that negative sign actually goes with the 9. So I got a 6 and a minus 9. So I got 6 and minus 9, and then I do that, and then I got to calculate it. So if you guys remember, I'll write it out just one time, but then you guys should just calculate it. So I'm going to multiply this diagonal. So it'll be a minus 18 times a minus 9 minus, and then I'll multiply that diagonal. This will be 6 times 6. So I got whatever this is minus 36. So somebody give me a value for D. If anybody calculated that, give me a value for it. I don't have my calculator, so you have to tell me what it is.
126.
Okay, somebody said 126. All right, so I'm just going to put this off in the corner just so we have the value that D is equal to 126. Now, if you remember from last time we made the video, last class, see if you can set it up to solve for IA. Now, we got 10 minutes, so we're going to go through the determinants kind of fast. So hopefully this 2x2 determinant you can do is pretty simple to do. You go ahead and set it up. I'll set mine up, and then you see if you agree with what I'm doing. And then we'll calculate it. Okay, so I'm looking for IA. So what we said was whatever coefficient you're trying to solve, you take the answer, I call it the answer column in class. You take that and you substitute for the coefficients of the variable we're looking for. So since I'm looking for IA, instead of writing the minus 18 and the 6, in this place I'm going to write 84 and 21. So IA is going to be 84 minus 21, and then this stays the same. I got a 6, and I got a minus 9. But you got to remember, you got to divide that by D, which we said was 126. Now, I won't write it out. I just don't have enough room on this little board. So I need somebody to go ahead and calculate that for me. Give me a value for IA.
-5.
Okay. -5. Anybody else get -5? I think that was Kevin. One more person agree? Okay. I got at least a couple people that say. Now, the significance of the negative sign. What that means is that we assume the wrong direction for a loop current. So what you got to do is we assume the loop current was moving in the clockwise direction. If you get a negative number, you just reverse it. So what I'm going to do is I'm going to erase this, and I'll write this as 5, but I'm going to reverse the direction because I got a negative number. So instead of 5 going clockwise, I'm going to write it as 5 going the other way. Okay, so that's a pretty simple step, but it's important that you understand the significance of a negative sign. So now I'll be quiet. I want you to go ahead and solve for IB and write your loop current in there with the direction and magnitude, and we'll see what you get. I'll set up the determinant on the board, but you go ahead and calculate it. Give me a second to write it before you say the answer. Okay, so I'm solving this time for IB. I'll leave these coefficients as they are. So it's minus 18, 6. Since I'm looking for IB, I'm going to substitute the 84 and the negative 21 for the 6 and the minus 9. So I got 84, I got minus 21, and you got to remember to divide that by D, which is 126. So give me a value for IB.
-1.
-1?
Yeah.
Okay, anybody else get a -1? If you got a -1, you can say something on here.
Yes.
Okay, all right. So what that means is we assumed again that the current was going clockwise. We got to reverse it. So I'm going to write down here, get rid of this. We got 1 amp. But since it was negative, I got to reverse my assumed direction. I assumed the wrong direction. Actually, it's going the other way. All right, so once we do all of that, so now what we got to do is just look at the current in each individual resistor. Now, if you, let me clean this up. If you look here, the only current that's going through R1 is the loop current, 5 amps, and it's going counterclockwise, so I'm going to erase, well, no, I won't. I'll show it in green. So what I have is 5 amps flowing in that direction. And the only current going through R2 is the loop current we said was 1 amp, and it's going counterclockwise. So I have 1 amp in this direction. And the only thing I gotta be careful of is this one. I got two currents. I got one loop current of 5 amps going up, the other loop current of 1 amp going down. So I gotta take the difference between the two. I got 5 amps going up, 1 amp down. I actually have 4 amps. 4 amps going up. Through the center resistor like that. And again, well, first of all, look at your superposition and make sure it agrees with what we got here. I think the numbers are the same and directions are the same. But again, the only thing I can ask you for is voltage drop or power. Well, you have the current, you have the resistance, you can give me voltage drop. You have the current, you have the resistance, you can give me power. There's nothing that I can ask you for that you couldn't give me once you get the current, direction, and magnitude to each resistor. Okay? So this is an example of mesh analysis. Now I got about 4 minutes. I want to give you another problem to do. So copy this down. And I'll work this during the next video, or maybe you can tell me what you got for an answer. So hold on a second. $60, 30, 20. 60, 30, 20. All right, so what I want you to do is to solve this problem using both methods. Solve it first using superposition, and then I want you to solve it using mesh analysis. Now, I don't know, I just don't have a lot of room on this board, so I don't think, probably what I'll end up doing is just solving it by hand and putting the solution up to see if you got it. But I do want to, we'll look at it on Monday. I do want you to see if you can solve it and get both methods to agree. And that's a really good way to do these problems, to solve it. Eventually, you'll know 3 ways to do it. And a good practice would be to do it all 3 ways and make sure that all 3 ways agree with each other. And you'll see that somebody asked a question, is it either or? Well, the good part about it is you'll see some problems are easier to do with superposition. Some, this is easier. The disadvantage of superposition in my mind is you have to keep drawing the pictures. You saw how quickly I filled the board up. Well, here you draw the circuit one time, the math does all the work. If you guess the wrong loop current, big deal, you just reverse it. And then I'll show you another way. Each method's going to have advantages and disadvantages. Now, I kind of favor this, but sometimes I'll use superposition depending on what I'm trying to do. When you deal with amplifiers, you want to see, you'll have an amplifier that has more than one voltage source in it. If you want to see what a certain source is doing, you got to use superposition. You can't use it this way. This is almost like magic. It's like the math does all the work. With superposition, you can actually see what each voltage source is doing. So I think that's more intuitive. So again, the more ways you know how to solve a problem, the better. It's not either or. It's the more tools we have in our toolbox, the more powerful you are, the more you can do. So guys, if you have any questions, I guess send me a text, or you can email me, but I don't check my email like I should. I'm saying this on video, so they're going to catch me saying that at Cincinnati State. I should check it more. But send me a text. And Kevin, did you ever send me your number? Are you still out there?
Yeah, I sent you my number.
Okay, because I think might have a solution, but I'm gonna call you here when I get done, because I think I might have a solution to your problem. But we gotta either be in front of a computer or we gotta be together. I'm looking at the computer. I should be looking at the camera. So you guys have a great rest of the day, and if you have any issues or problems, let me know. And I'm trying to do the best I can in my basement of my house. I'm not really comfortable. You probably can tell I'm very uncomfortable and disorganized because I'm not used to teaching this way, but I'm sure it'll get better. I just need a couple
Okay.
days. You guys have a good one, and I'll see you later.
Hey, Ron, did we have a test coming up?
You do have a test coming up. I haven't written it yet. I have a test, but I can't give you the one that I have because so I got to make a special test to do this online thing. So who was that? Sam? Who was that asked that?
Steve?
Steve. Okay, Steve. I won't do it. What's today? Friday?
Yeah, today's Friday.
Probably I'll put it up maybe Wednesday. Wednesday. All right.
What about the multi?
Okay.
And I'll say more about it on Monday. All right, guys. Have a good one.
Oh, hold up.
I was.
But what about the multism lab?